Hello, and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today, we're going to be looking at the second part of our transformation of single random variables lecture series. We're going to be looking at what I commonly refer to as the inverse problem. So what do I mean by that? Here's sort of the situation. We are going to assume that we know a starting random variable's probability density function. We're going to know this. And we're going to assume that we know another desired probability density function. We're going to know this part too. And what we want to do is find a transformation that will unite them. All right? What we want to do is take data that is somehow distributed according to probability density function little f sub x, transform that data, and end up with data that is distributed according to the probability density function little f of y. We're going to make a couple of assumptions here. One, we're going to assume always for this discussion that my probability density function for x is uniform on 0 to 1. It's going to be over here. This is the probability density function that we are always going to assume for this discussion. All right? It'll never be less than 0. It'll never be greater than 1. The probability density function, of course, always has unit area, meaning that the peak value of my probability density function is 1. That's pretty much the simplest possible probability density function that you're going to encounter. Uniformly distributed on 0 to 1. Why is this interesting to me? There are random number generators built into your calculators. So for example, if you look on your calculator somewhere, if you have a scientific calculator, you're probably going to find a button that's got RAND on it somewhere, something to that effect. If you press that button 1,000 times, you're going to end up with a whole bunch of numbers uniformly distributed between 0 and 1. In any interval between 0 and 1, you're going to get an equal number of values as long as that interval moves around and remains a uniform size. All right? Calculators have built-in random number generators. MATLAB has a RAND, R-A-N-D function. If you run the rand.m function 1,000 times, you will end up with 1,000 numbers, all of them between 0 and 1. They'll be uniformly distributed between 0 and 1. Okay? This discussion is going to be extremely useful to us when we get into two later topics. One is the computer generation of random variables, and the other is Monte Carlo simulation. Monte Carlo simulation is a process by which we can examine the random outputs of systems, for example, based on random inputs. Well, what happens if I have a noise signal that is Rayleigh distributed? Maybe my noise voltages obey a Rayleigh probability density function. Well, MATLAB does not have a built-in Rayleigh probability density function generator. Neither does your calculator. How can I create data that's distributed according to a Rayleigh probability density function and run that through a system model to determine the behavior at the output? Well, what you're going to learn in this lecture will allow you to do that. We're going to take something very, very simple. We're going to take data, in effect, that is uniformly distributed on 0 to 1. We're going to come up with a way of transforming that with a simple function to get data distributed according to any other probability density function we might be interested in. I said we were going to make a couple of assumptions. The first assumption is that we're always going to be looking at an input PDF that's uniform on 0 to 1. The second assumption is we're always going to be looking for monotonic transformation functions. We're going to look for the simplest possible transformation function that will yield the desired results. Okay? And by monotonic, I mean g of x is always going to be always increasing or always decreasing. It's not going to go up and down, no transcendental functions, nothing like that. Okay? All right, let's do the math. First of all, remember from the last video that my transformed probability density function equals f of x times the absolute value of derivative of x with respect to y, where we always substitute x equals g inverse of y. Written perhaps in a more compact form, we would say it this way. All right. Now, let's take this down one step and acknowledge the fact for this case, our probability density function in x is always uniform on 0 to 1. So my probability density function for y can be written as the absolute value on the range 0 to 1, the probability density function for x equals 1, and so I just end up my probability density function for y is just the absolute value of the first derivative of g. And then it's 0 everywhere else. All right? So the next step I want to do is I want to get rid of the absolute values. This will be, let me just write it down, then I'll dissect it a bit for you. So, if my derivative in this middle step is positive, then I can just simply throw away the absolute values. If the derivative happens to be negative, I can make it positive by throwing in a minus sign. That's equivalent to an absolute value. All right. In both cases here so far, x is on the range 0 to 1, and then it's 0 elsewhere. All right? So the next thing I want to do is I want to get rid of my derivatives, and I'm going to do that by integrating both sides. So I'm going to integrate both sides, and I'll do that on the next page. I'm going to integrate both sides. And what I get is g inverse of y equals, I'm just going to go ahead and set that equal to x. Remember, I'm looking for y equals g of x. So g inverse of y equals x. Integrating both sides, I get integral from minus infinity to y, f of y dy. And that, of course, is my cumulative distribution function for y. And the next piece would be negative integral from minus infinity to y of f y dy, and that would be the negative of the cumulative distribution function. And of course, this is true for dx dy positive, and this is true for dx dy negative. All right? And always we remember that x lies on the range 0 to 1. All right. So let's remind ourselves now about the behavior of the cumulative distribution function. The cumulative distribution function always varies between 0 and 1, meaning that if I set x equal to the cumulative distribution function of y, I always get x values that lie on the range that I'm interested in. Moreover, a proper cumulative distribution function is an always increasing function, meaning that dx dy is positive. For that reason, there's simply no reason to look at the second part of the result inside of the curly braces. I can just simply ignore this part. It doesn't apply. The upper part of the result in the curly braces is my actual solution that I'm interested in. All right. So x equals cumulative distribution function for y. Conversely, I can write my transformation function for y equals the cumulative distribution function inverted, evaluated at x. That is my final result. And of course, x is always uniform on 0 to 1. So what that tells me is, if I take a random number generator, for example, and I calculate 10,000 points that are uniformly distributed on 0 to 1 and plug them into a function which equals the inverse of the cumulative distribution function for y, I will get out an equal number of points in y that are distributed in any way I choose. Okay? All right. Let's do several examples. First, I'm going to assume that for all these examples, I'm going to assume the same, that my cumulative distribution function for x is uniform on 0 to 1. And in this particular case, excuse me, I got a frog in my throat. I'm going to assume that my probability density function for y is 2e to the minus 2y u of y. This is clearly an exponential PDF, and we sketched it. Would look something like this. Okay? Area is always going to be 1. If you integrate this out, you get area is always 1. Okay? It's a proper probability density function. So what I want to do is move x, which is uniform on 0 to 1, into y, which is exponentially distributed. The first thing I need is the cumulative distribution function for y, and then I'm going to invert that. We've done this before, but we can do the math again. Cumulative distribution function is the indefinite integral of the probability density function. Plugging in my PDF, I get this. I get 2 times the integral from 0 to y e to the minus 2y dy. Now, you'll notice that my step function affects the lower limit. All right, my probability density function has no value less than 0. All right, so this is minus 2 over 2 e to the minus 2y evaluated from 0 to y, and this equals 1 minus e to the minus 2y u of y. Once again, this step function does not come out due to the integration. It comes out because I know that my random variable y, and I just noticed that I made a mistake up here. Let me go back and fix this. On my curve, that should be a y. I'll make it in red to highlight it. That should be a y. And up here, this should be the cumulative distribution function for y. Probably all of you saw this when I did it. Sorry about that. And let me fix my arrow. All right. So, the reason that my cumulative distribution function in y has to have the step function is because y is never less than 0. Y is always a positive value. Okay? All right. So now we know what the cumulative distribution function is. We'll set that equal to x. And then we'll invert that, and we'll find that my transformation function is this. That's that. And in all cases, we will have that x is uniformly distributed on 0 to 1. This is my final result. Assuming that x is uniformly distributed on 0 to 1, if I calculate a bunch of x values using a random number generator, oops, I forgot my natural log. Negative 1/2 times natural log. That's the result that I'm looking for. So if I calculate a bunch of random values between 0 to 1 for x, and I plug them into this relationship, negative 1/2 times the natural log of 1 minus x, I will end up with data that is distributed exponentially according to that function. Okay? All right. Let's do another example. Once again, I'm going to assume that x is uniform on 0 to 1. X is uniform on 0 to 1. And I'm going to let y be a random variable that has a general Gaussian probability density function. This is a general Gaussian. All right. Now, before I go any further, I'm going to tell you in MATLAB there is a rand n function. Rand n. However, this rand n, and the rand n function gives you Gaussian distributed data. The rand, R-A-N-D dot M function gives you data that's uniformly distributed on 0 to 1. The rand N function, N stands for normal. Another name for the Gaussian distribution is the normal distribution. The rand N function, however, gives me data that is distributed according to a 0 mean unit variance PDF. All right. MATLAB does not have a built-in random number generator that will allow you to create data that is distributed according to a general Gaussian with any mean or standard deviation. So, I made a claim in an earlier video that the Gaussian distribution is one of the more common distributions that you're ever going to run into. It's really important for us to be able to transform uniformly distributed data using the rand function into a general Gaussian set of data with a general Gaussian probability density function. So how do we do that? Well, once again, I need to know the cumulative distribution function. I've created this for you earlier. The cumulative distribution function for my general Gaussian is 1 minus the Q function. I evaluated it, y minus m over sigma. And I'm going to go ahead and I'm going to set that equal to x and invert it. And very simply, y is the inverse cumulative distribution function for y evaluated at x, and that is sigma times q inverse 1 minus x plus m. Always under the assumption that we're talking about x as a uniform random variable that's uniformly distributed on the range 0 to 1. Okay, this is the final result for this example. If I use the rand function, for example, in MATLAB and create 10,000 data points or 100,000 data points and apply this transformation function for an arbitrary general Gaussian with any mean and standard deviation or variance, then I can get y, which is distributed according to that general Gaussian function. All right? Let's do another example. Got 2 more examples for you. Once again, x is going to be uniformly distributed on 0 to 1. X is going to be uniform on 0 to 1. And this time I'm going to have y is going to be uniform on a different range, A to B. That's pretty common. That's what a uniform probability density function looks like in general, where my random variable y is uniform on the range A to B. And of course, the amplitude of this PDF is chosen so that the area is 1. Okay, all proper probability density functions have an area equal to 1. All right, well, I need to know what the cumulative distribution function looks like. We can just sort of piece that together. We've talked about it earlier. The cumulative distribution function for y will increase linearly from A to B from 0 up to 1. So above b, my cumulative distribution function will be exactly 1, and it will vary linearly, it will increase linearly from a to b. And then it'll be 0 for for y less than a. All right. Written as a function, that is my now let's just leave it at that. That's what I need. All right, my cumulative distribution function in the range from a to b, it's a straight line. All right, and it equals 1 for y greater than or equal to b, and is 0 for y less than or equal to a. All right, so what I want to then do is I'm going to set my cumulative distribution function for y equal to x, and invert that, and I'm going to get y equals the inverse cumulative distribution for y evaluated at x, and my result then is that's my final result, assuming always that 0 is less than or equal to x, less than or equal to 1. That's it. That is the transformation function that will allow me to transform data that's uniform on 0 to 1 into another uniform random variable that is uniform on the range a to b. Okay? All right. One last example. Once again, I'm going to assume that x is uniform on the range 0 to 1. And this time I'm going to assume that my probability density function for y is a Rayleigh probability density function. It's going to look like this. Looks like this. Kind of increases linearly, peaks out, and then has a long decaying exponential type tail. Has no value for y less than 0 due to that step function. So earlier in another video, I'm not going to do all the math now, I found that the cumulative distribution function for y equals 1 minus e minus y squared over 2 sigma squared times that step function. All right? All right. So what I'm going to do is I'm going to set this equal to x and invert it. And I'm going to get y equals all right. And you'll notice here I don't need a step function for x, since x is never less than 0. Or greater than 1. In fact, x is always on this range. Okay? So, that's my final result. All right? That is the way by which I would take data that is uniformly distributed on 0 to 1 and create any arbitrary Rayleigh probability density function. Let me just write this up here. This is a Rayleigh PDF. Okay? MATLAB, for example, does not have a built-in Rayleigh probability density function. We would have to generate Rayleigh distributed data on our own using a uniform random number generator. All right. That's all the examples I have for you for today. It could be worse. I know I've been giving you a lot for the past 2 lectures. I hope that you're catching on to this. It's really powerful stuff, especially when we get into computer generation of random variables and Monte Carlo simulation. We're going to see this quite a bit. And if you're having trouble with this at this point, always do ask me questions and play back the videos. Ultimately, hang on until you catch on. All right, that's all I have for you today. As usual, if you have any questions, please contact me at your earliest convenience, and I will do everything I can to answer your questions as fully as possible. That's all for today. Bye-bye.